Hello friends, welcome again to the tetrahedron chemistry classes. So in today's class I am going to discuss the basic concepts involved in the infrared spectroscopy, and in the subsequent classes I will cover the entire infrared spectroscopy with all the detailed interpretation of the IR spectra and the different things which are important for a student to understand in the infrared spectroscopy. But the methodology of teaching IR spectroscopy I will adapt differently actually. What is the meaning of that? See, whenever you read or you try to learn the infrared spectroscopy from the textbooks, they actually the books generally give the different sequences of IR spectroscopy, or the different sequences which actually must be taught during the IR spectroscopy. But I'll start this infrared spectroscopy in the different way. Why actually I am adapting the different methodology, right? The reason is that when we during the viva voce, when we ask to the students what are the 3 or the 4 uses of the infrared spectroscopy, so generally they are not aware about the different applications of the spectroscopy, infrared spectroscopy, not only for the infrared spectroscopy but for all the other spectroscopy techniques also. So my way of starting infrared spectroscopy is like that. First I will explain you why actually we study the infrared spectroscopy. Okay, so before starting this I should mention the date. So today is 9th of March 2023. Okay, so this is my first lecture on infrared spectroscopy in the today's class. Okay, so here you see infrared spectroscopy. Why study infrared spectroscopy? So I have summarized all the points here. Actually what you can do, you can take the snapshot of this. So determination of the force constant from the IR spectra to know the bond strength, thus bond length can also be calculated. The meaning is that, see, later on you will learn these things in the pretty much detail, but right now you can summarize these points point wise. Okay, so here if you have the IR spectra, so with the help of the IR spectra, what you will get the IR stretching frequency, and once you know the IR stretching frequency, then by using the Hooke's law you can determine the bond strength. Okay, once you know the bond strength of that particular bond, then it is very easy to calculate the bond length, right? So there are the few examples, right? If you have your hydrogen chloride HCl, then the force constant for this your molecule is 480 Newton per meter. Similarly, if you have the hydrogen fluoride, for this force constant is your 870 Newton per meter, right? And it is quite obvious because hydrogen fluoride is the more polar one. Fluorine is the most electronegative element, right? When compared to the chlorine, it is very highly electronegative, so its bond strength is quite high. Definitely its bond strength would its your force constant would also be high. So this is the one way. If someone asks you what is the application of the IR spectroscopy, then you will straightforward reply that with the help of the IR spectra we can detect the bond strength, which will be useful to calculate the bond length of particular bond, right? But please remember, the bond must be the molecule must be polar, because only polar molecules we can study in the IR spectroscopy. Later we will see the which kinds of the molecules are IR active, which kinds are not. Okay, now second important your second important application, right? What is the application is that, right? For example, say if you are having the paraffin wax, if you have your paraffin wax, what is the meaning of the paraffin wax? That means you are having the long chains of the hydrocarbons, right? So you are having your CH3, and then your CH2, and then your CH2, and then your CH2, and then your CH3. So for such kind of the compound, if you check the IR spectra, then in the IR spectra you will find the stretching vibrations of your CH bonds, which actually resonates between 2900 to 3000 centimeter inverse, right? But if you are, say for example, if you have this paraffin wax and little of your carbonyl compounds, say for example the ketones, if you added the little bit of the ketone to it as impurity, then what will happen if you take the IR spectra of this one, right, this mixed compound, then definitely at near about 1700 centimeter inverse, okay, you will get another band which actually indicates the presence of the carbonyl group. So very easily you can find the impurities also with the help of the IR spectroscopy. So determination of the purity of a particular compound. If a small quantity of the ketone, as I have explained here, is added to the paraffin wax, then IR spectroscopy will detect the presence of the ketone by showing an absorption band near 1720 centimeter inverse, right, or you say roughly you can say the 1700 centimeter inverse, okay, and this 1700 centimeter inverse is actually the presence of the carbonyl group. Later we will discuss the different types of the carbonyl groups, if it is present in the acid, if it is present in the ketone, or in the aldehyde, or in the acids, amide. They will have the different values, right, but it will near about your 1700, or it will range from 1700 to 1800, right. So this is very important to detect the impurity, right. And then your third application, of course, identification of the unknown compound. However, it is almost impossible to actually completely identify your unknown compound with the help of the one single spectroscopic technique. As I already told you in my previous classes, you need different kinds of the spectroscopic techniques to characterize a particular molecule, but in the some way your identification of an unknown compound can be done with the help of the IR spectroscopy also, and this is generally done in the fingerprint region, right, and we'll use the fingerprint technique to actually confirm the presence of the particular type of the compound, right. What fingerprint technique actually generally do, this involves the matching the spectra of the unknown compound with that of the known compound. For example, say if someone is very beginner in the organic chemistry, right, and say if a particular student who actually are not interested in the chemistry, or finds difficult to understand the chemical concepts. For example, you are having this cyclohexanol and you are having this here phenol, right, these two molecules, and you can see many times you can see the beginners or the students which are not very much keen to learn the organic chemistry, they often made this mistake, right. They actually think this cyclohexanol and this your phenols are the same thing, right. However, these two are looking quite closely, they are actually looking very similar. So but you can see here the absence of the bonds are there. So this is the benzene ring, this is cyclohexene ring. If you run the IR spectra of these two compounds, they would be quite different actually, right. So this is very important in the fingerprint region. If we have say some confusion about the two different kinds of the compounds and they are looking like the same, so what we can do, we can run their spectra in the fingerprint region, and that fingerprint region will actually will give you the different spectra for the different compounds, right. You should remember this point. And then there comes the next point, identification of the functional group in the organic molecules. If you have the organic molecules may have the different kinds of the functional groups, right. And see, this is the most important actually application of the IR spectroscopy. We can find the different kinds of the functional group. For example, if you have the functionality of this alcohol, right, this OH group, so you will find a band near about 3600 centimeter inverse. For carbonyl, I already told you, you can find this you are at 1700 centimeter inverse, right. And there are many other functional group also, right, which you can detect with the help of, which you can identify with the help of the IR spectroscopy. We will discuss all these things in pretty much detail in the subsequent lectures, okay. Now next is point 5 actually, to distinguish between the intra and intermolecular hydrogen bonding. So later I will discuss this thing in pretty much detail, but right now you can understand in that manner. If you have if you want to find whether the hydrogen bonding if present in the molecule, it is of intra type or the inter type, then you can use the IR spectroscopy. So for time being, you can remember this point: intramolecular hydrogen bonding actually is not affected by the dilution. That means if you have the intramolecular hydrogen bonding in the molecule and you are diluting the sample, then the intramolecular hydrogen bonding will not change and your IR spectra would remain the same on the dilution. But intermolecular hydrogen bonding, actually the dilution dependent, or you can say the concentration dependent. That means if your hydrogen bonding is the intermolecular type, then the shape of the band and the position of the band will change if you keep on diluting your sample. This is something very, very important which you should know. And number 6 is structure elucidation. So this is another very, very important point, because this IR spectroscopy gives the valuable information regarding the molecular symmetry, dipole moments, and the bond lengths, bond strength, as I explained in the point 1. So if your molecule is perfectly symmetric, then it would not be your IR active molecule, and you can very easily find the symmetry. Please remember, your perfectly symmetrical molecules actually gives the very few peaks in the NMR also. And if your molecule is perfectly symmetrical, then IR you cannot run you cannot actually observe the IR spectra for such compounds, right? And dipole moment is very, very important factor, right? If your molecule is having the dipole moment, only then it would be IR active. Later we will see. So it's, in the elucidation of the structure, these points actually are very, very important. So these six applications of the infrared spectroscopy, each and every chemist should know actually, right? Say in your viva voce, if someone asks you what are the different possible applications of the IR spectroscopy, then you will straightforward reply, and you can use these 6 points to answer your question. Okay, and after that, see, once you have completed this, you should know the range of the IR spectroscopy. So IR spectroscopy basically involve the transition between the vibrational energy of the molecule on the absorption of the IR radiation, falling in the range of 4000 centimeter inverse to 667 centimeter inverse. So please remember, this vibrational spectroscopy is infrared spectroscopy is also known as vibrational spectroscopy. Vibrational spectroscopy. Why vibrational spectroscopy? Say for example, if you have this particular molecule, right, and if you actually shine IR light to this molecule, so what will happen? The vibrational energy level of this molecule will change, right? And this change in the vibrational energy level is responsible to give the IR spectra. That's why it is also known as the vibrational spectroscopy. And range, you know, roughly you should remember this range. It is actually in between the 4000 to 667 centimeter inverse. So here are the different regions. So here you can see what I can do. I can underline it. These are the regions, wavelengths and wave numbers. Okay, you should know this thing. Say near IR region is having the wavelength which is given in the micrometer here, 0.8 to 2.5 micrometer, and you can very easily convert this 0.8 to 2.5 micrometer range into the centimeter inverse, which is the wave number, right? If you don't know how to convert this wavelength into the wave number, right, and all other different things, so I have already made a lecture on this. So in the description box I am giving you the link. You can go through the link if you don't know how to convert these things into one another, right? And also at the right top corner the link is flashing. You can click on that link to actually go through this particular lecture also. Okay, So this wavelength very easily can be converted into the wave number, and if this 0.8 to 2.5, if range is this wavelength is there, then you can easily convert this into the 12,500 to 4,000 centimeter inverse. And this region is important for the overtone bands. See, in the IR spectroscopy, actually you have the fundamental bands, you have the overtones, you have the hot bands, right? All these different kinds of the bands are there. So when you have the overtones, right, then definitely the range would be like that. But we are not very interested in the overtones when we interpret the IR spectra, because you see, these overtones are of very low intensity. Their intensities are not very high, okay, because they are actually what you can say, the harmonically forbidden bands. If they are harmonically forbidden bands, that means their intensity would be very low, and we are not interested in this. So this range is not very important for us, but as a student you should know this thing, okay. And then after the near infrared region, there comes the middle IR region, which actually extends from 2.5 micrometer to 15 micrometer, and this range is very important for all the chemists. Please remember, this is the most important range for any chemist, very important range, okay. And you can convert this 2.5 to 15 micrometer into the centimeter inverse, that is the wave number. Then you will find the range is 4,000 to 667 centimeter inverse, which actually I have already explained you here actually, right? And when you have this range, then you can find the vibrational spectra as well as the rotational spectra. So rho vibrational spectra you can find in this particular region. So why we find the rotational spectra along with the vibrational spectra? Because inside the vibrational spectra there are large number of the rotational spectra, and when you shine IR light to the molecule, then their vibrational quantum number changes, and when vibrational quantum number changes, then automatically inside them there are rotational quantum numbers also. They actually automatically change with the change of the vibrational quantum number. So this range is very important, and later when we interpret the IR spectra, you will find all the results actually you will find in this particular range. This is very important to note that. And after that there comes the far infrared region, which extends from the 15 to 200 micrometer, and you can convert this into the 667 to 50, right? This, in this range you can convert this, right? And then I actually missed some this thing here, so this can move like that. Oh, okay, no, I didn't miss anything. So this is just like this, 667 to 50, right? And in this region far, we actually only obtain the rotational spectra, but we are not doing it, the microwave spectroscopy, so we are not interested in the far IR region. And one another important thing which you should keep in mind, this far IR region is important for the inorganic species. But right now I am discussing the organic spectra or organic spectroscopy. That's why I am interested only in the middle IR region. So I hope this first slide is clearly understood, and this is very helpful and very important for you. And this is my personal advice to the students: whenever you are start learning your infrared spectroscopy, you should actually learn like that, which actually I am explaining here actually, right? This is something very important. Now moving to the next slide. Okay, now my next slide is like that. So what it says, okay, conditions for the vibrational spectrum. So I can write here conditions for the vibrational spectrum. Vibrational spectrum means your IR spectrum. Okay, just like that. So that means which kind of the molecule. See, when actually this vibrational spectra you can get if you shine by IR light onto the molecule. First of all, vibration must involve a change in the dipole moment. See guys, whenever I am discussing the dipole moment, that means I am dealing with the polar molecule. So only polar molecules would be your IR active, and only those polar molecules which actually have which actually lacks the symmetry. Perfectly symmetrical molecules generally don't have the dipole moment, and they are not IR active. So what happens actually, you see, for example, if your molecule is like that and it is vibrating, this molecule, say it is vibrating like that, okay, and when you shine IR light to it, then this will vibrate like that, okay. So if this is representing the dipole moment, and after absorbing the IR light, if your dipole moment is changing like that in the great way, only then you can observe the IR spectra or the vibration spectra, otherwise not, okay. And next important thing which you should know, a molecule undergoing vibrational change within an electronic state must satisfy the selection rule of delta V equals to plus minus 1. Delta V, see, V is the vibrational quantum number, delta is the change in the vibrational quantum number. So this is actually the selection rule, okay, which actually comes after the rigorous mathematics, rigorous quantum mathematics, okay. When we apply the concept of the quantum mechanics to the spectroscopy, then we will get this we will get these selection rules. So in IR spectroscopy, the selection rule is like that: your vibrational quantum number will change only by the 1 unit, see, 1 up or 1 down. But we generally actually, this is guys, this point is very important for you. See, del V equals to plus minus 1, okay. That means what can happen, if your molecule is in the zero vibrational state, then it can go to the V1, just like that, right? And if it is in the first vibrational state, it can fall down to the V0. So please remember, this actually is the emission spectra. This is emission spectra, and we are not interested in the emission spectra, because in IR spectroscopy we actually detect the absorption spectra. So del V equals to minus 1 is not applicable in our case. In our case, we are only interested in the del V equals to plus 1. How? See, when it is going to from 0 to V1, so you can calculate this V equals to what? 1 minus 0 equals to 1, right? This is the absorption spectra, right? But when you are having, say, when you are dealing with this one, right, say for del V equals to minus 1, how I am getting this? So earlier my molecules are in the first vibration state and they are falling back into the zero vibration state. So this is the final, I can write F this one, and this is the initial, right? If you determine the delta V, so this should be your 0 minus 1, that is equals to minus 1. But this is emission spectra, please remember, this is emission spectra, and we are not interested in the emission spectra. So del V minus 1 is not applicable in our case, though the selection rule is like that, del V equals to plus minus 1, but we are interested only in the del V equals to plus 1, because we are recording the absorption spectra. You should remember this point, this is very important, right? However, other transitions are also possible, right? Say your molecule from the zero vibrational state go to the second vibrational state, and it can go to from first to 3, but in that case your del V equals to plus 2, or you can see in that case it is the plus 2 actually, right? But this plus 2 transitions are not very important, because they don't occur for a strictly harmonic oscillator. Harmonic, see, later we will discuss the harmonic oscillator. Why actually, I will discuss each and everything. Why actually we are involving this physics into the molecules, why the harmonic oscillators we are selecting, all these things. I'll discuss these things in pretty much detail, but right now you can understand in that manner the vibrational transitions from 0 to 2, 1 to 3, right, or 2 to 4, where del V equals to plus 2, they are harmonically forbidden, so we are not interested in it. And then the frequency of the emitted or the absorbed radiations must satisfy the Bohr's condition. Bohr's condition is what? Del E equals to h nu. This is the Bohr's condition, and one more way of writing this Bohr's condition is like that. If you have, say for example, del, I can change the color, del E equals to nu bar. Nu bar is the wave number which is in the centimeter inverse. So Bohr's, this is the Bohr condition, del E equals to h nu, and this is also the Bohr condition, del E equals to nu bar, because the most fundamental unit which actually generally used in the IR spectroscopy is the wave number. So you should remember this thing. So frequency of the emitted or the absorbed radiations. There is no question of the emitted because we are not interested in it. See, however, we cannot say that there is no question. This would always be there, but we are not interested in this actually. So you should remember this point. The frequency of the absorbed radiation must satisfy the Bohr's condition, and Bohr's condition is del E equals to h nu and del E equals to nu bar. Later I'll discuss all these things in the pretty much detail, right? So this is something very, very important for you. Now moving to the next. Okay, now what actually I am going to explain you here are IR active molecules and inactive molecules. So first I am discussing here, say, IR active molecules. I am discussing IR active molecules. So what kind of molecules are actually IR active? So please remember, molecules with permanent dipole moment. Molecules with permanent dipole moment will be IR active. For example, if you have the HCl molecule, right? You know this chlorine is electronegative, so this is negatively charged, this is positively charged, right? And its dipole moment will lie just like that. So it will have a net dipole moment value. Dipole moment generally we indicate with the mu, right? This will have the net dipole moment. So this would be your IR active. And in the same way, you can explain HF is also IR active because it is polar. Water is another very, very important one. Your methyl chloride, which is CH3Cl, it is again your IR active. Compounds with carbonyl groups, they are IR active. Compounds with carbon single bond oxygen, they are also IR active, right? So many polar molecules because they have the permanent dipole moment. And the molecules, sometimes it may happen that the molecules actually is not having the permanent dipole moment, but the activity of the molecule, activity generally, we cannot use the activity because activity, you can confuse this activity with the active mass or certain like that. Activity means here actually in that case the activity means when the molecule actually is say vibrating. When your molecule is vibrating, then certain vibrations actually will induce the dipole moment in the molecule, and only those vibrations would be IR active, though the molecule will not have your permanent dipole moment, but they can be IR active. So please remember this point. There are certain molecules which as such don't have the permanent dipole moment, but some of their vibrational modes are accompanied by the change in the dipole moment. For example, if you have like you are having the carbon dioxide, okay, CO2, you know this carbon double bond oxygen, this is another carbon double bond oxygen. If you check the net dipole moment, so this will come in that direction and this will go in that direction, and you know this is the vector quantity, and this dipole moment is the vector quantity because it is having the direction as well as it is having the magnitude. So when the vector goes in the opposite direction, they cancel each other. So net dipole moment for this molecule would be 0. So according to the concept, it should be IR inactive, but it is not like that. It is actually somehow IR active. Why it is IR active? If you take the asymmetric, you see, for example, asymmetric stretch. I am writing asymmetric stretch. So later I'll explain you these things also, right? What are the stretching, bending, and all these things. So what is the asymmetric stretch? For example, this bond is compressing like that, and this bond is stretching like that. Okay, so what will happen? This will go in that direction, this will go in that direction. So somehow this molecule will have the net dipole moment value. And sometimes, say, if you are not very comfortable with this asymmetric stretch, then you can understand, however it is true, but if you are not actually grasping the things completely, then you can think another mode, right? So for example, this is your carbon, and say it is bending like that, this is bending like that, right? Okay, this will also induce the dipole moment into the molecule. That's why, though this carbon dioxide is having zero dipole moment, but some of their vibrations like asymmetric stretch or the bending vibrations may accompanied by the change in the dipole moments. That's why it is IR active. So thus the essential condition for a molecule to show the IR spectrum is that it must show a change in the dipole moment during the vibration. Okay, however, it is important the molecule must have the dipole moment, but sometimes it is not having this, but it can induce the dipole moment. This is something very important, right? This is something very important. Now, if you have understood these things completely, then we can move further. How we get the IR spectrum, and why actually we select the harmonic oscillator, all these things now I am going to discuss. Say for example, okay, just like that, right? So how I can get the IR spectrum? For example, say, see, first of all, in IR spectrum you should know this point. Your atoms generally considered as the balls, okay, and then your bonds, they are regarded as the springs. See, your spring actually, if you have any spring, and if you actually stretch that spring and you left that spring after stretching, you actually leave that spring, then it will vibrate like that. And molecules actually always, if you keep the molecule in the absolute zero, then molecules will also vibrate. So since both are vibrating, so we are considering the molecule, IR active molecules, as the combination of the atoms and your so combinations of the balls and the springs, which actually is the analogy, right? Balls for atoms and springs for the bonds. Say for example, you are having this atom and this atom, and they are connected with the bond. In actual practice, this is the atom, this is also the atom, and this distance is actually the bond. So what actually we can do in that case? Say for example, if I stretch this like that here, right? If I stretch this spring, so what can happen in the next instant? This atom will come here and this will come here, for example, right? And then you see bond is stretched like that, the bond is stretched like that, and this was the actual positions of the two atoms. So basically this actually difference and actually this difference, just like that. Say this is x1 and say this is x2. Basically this x1 and x2, they are the displacements. They are the displacements from the original positions. Okay, so what can happen when you have this kind of the situation, right? Then of course you can think about the harmonic oscillator. So a simple harmonic oscillator can be considered as a model for a vibrating diatomic molecules, because two atoms are there, so I am calling it as diatomic molecules. Okay, so what can happen, say for example, say this molecule is here and you are stretching. Say this molecule is here, right, and you are stretching like that, you are stretching this molecule like that. So what can happen, one restoring force would be actually applied on this system. How? And please remember, restoring force will always in the opposite direction of the stretching. Say for example, if you are stretching in this direction, then your restoring force would be in that direction. How? So this is actually the restoring force. This is your restoring force. Restoring force is a kind of the force actually which restores the your original condition, and your original condition were like that and you have stretched actually. So restoring force actually will push back these this atom to this position in order to get the initial stages, right? So this is the restoring force, this will apply in that direction, and here the restoring force will apply in this particular direction. You should remember this point, whether you are compressing the bond or say now this is the case of the stretching. Now if you compress the bond, compressing means say your atom is coming here and your atom is coming here. Okay, you are stretching like that. So original positions of the atoms were like that. Okay, and here you have actually compressed them. So this is the displacement. This is the displacement. You can call it as x3 and x4. Okay, so in that direction, since you have actually compressed or squeezed the bond, then the restoring force will be in this direction. Okay, in this direction. So here in the blue you can see this is the restoring force and this is the restoring force. So restoring force will always be in the opposite direction of the stretching or the compressing. If you are stretching the bond, then again it would be in the say opposite direction. If you are compressing the bond, again it would be in the opposite direction. And this is, see, this is exactly where the spring behaves. That's why this simple harmonic oscillator concept actually we can apply onto the diatomic molecules. Please remember this thing. Now I am going to discuss your diatomic molecule spectra. For this I need some space, so you can take the snapshot of this. I am erasing this. So this I have erased. So now I am going to discuss SHO model. SHO model. So what is SHO model? Where S stands for the simple, H stands for the harmonic, and O is the oscillator. This model I can choose it, right? So why actually I am choosing this, I can already explain to you this. I already explained all these things. Okay, because we can always take the bond and the atoms like that your spring and the balls. And whenever you are discussing this your spring and ball models, then obviously it will always follow simple harmonic oscillator. All the simple harmonic oscillators, they follow the Hooke's rule, or not rule actually, Hooke's law. Okay, difference between you should know the difference between follow. Sorry, again I missed here Hooke's. So I can write HOOK, Hooke's law. So what is the Hooke's law actually? What the Hooke's law says? Hooke's law says whenever you have stretch or the compress the bond, the restoring force would be directly proportional to the displacement. Please remember this point. The force spring exerts on a particle is proportional to the displacement from the equilibrium position. As I have already explained you, when your molecule is in the normal state, room temperature, or say they are vibrating like that, So it will have the equilibrium position, the displacement, or that means the bond length actually, right? And if you stretched it and if you compressed it, then the force the spring exert on a particle would be proportional to the displacement. This you should remember, very very important, from the equilibrium position. Okay, so this is just like that. And if you remove the proportionality sign with the equality sign, then you will get the proportionality constant, and this proportionality constant I am calling it as F, and X is already there. And you know this F is what? The restoring force, and restoring force is always in the opposite direction, so we can put negative sign here. This is something very very important, okay, which you should know. Okay, so this is your force constant, and restoring force is always in the opposite direction, that's why we can put negative sign here. This is something very very important. So when you have this kind of the situation, then you can determine the potential energy of that particle, or say of that molecule. So how we can determine the potential energy? So for potential energy, what you can write? Vx. Why x? Because x is the displacement, that means the potential energy when you are say restoring force actually, or is the function of the your displacement, then definitely the potential energy of this particular system will also the function of the displacement Vx, and that Vx would be equals to negative of, I can write, F into dx. This is one way. And then what you can do, this was your F. What you can do, you can put the see this is the equation number 1, this is the equation number 2. So what you can do, you can put the value of the F, which is your minus Fx, to in this particular expression. So when you put this value here, then you will find V of x equals to your Fx into dx. So guys, please remember this particular point. So see, these lots of f's are there, they can actually confuse you. So what I can do, I can replace this f with the k. So I can replacing this f with the k. Now it is little bit better, kx, right? So what you can do, you can integrate this. If you want to integrate this, what you can do, you can put the integration sign there, and then after integration you will get v of x equals to half of kx square, right? See, I can understand for the biology students who actually haven't studied the mathematics after actually class 10, is find difficult how to actually how to get this expression from this. So basically this is the simple formula of the integration which you can apply here, and this formula is just like that. Say for example, I am giving you this thing. So for example, say this is integration of 4 x to the power of 7 of the dx, right? So what actually in this case we can do, we can write this 4 as such, divide this 4 by 8, because 7 is there, you can add 1 to it, so this is 4 by 8, and x to the power 7, so you will x to the power 7, you will add 1 more to the 7, it will become x to the power of 8 plus the constant of the integration. What this will give you, this will give you half of x to the power of 8 plus c. In the same manner, if you apply this concept here, actually what was like that, it was like that, integration of the kx, okay, and this is say your dx. So what you can do, you can write this k here, okay, and because and then you can put this x, that means your x square you can put here, and you will divide this by 2, so that will give you half of kx square. So this is half of kx square. So this is kind of your what we can say, the maths corner, right? You can write it as maths corner, and this is especially for the biology students. If you remember this formula, then you can easily get this particular equation from that equation. So this equation you can Call it as the equation number 3. This is your equation number 3. Okay. Now what you can see in any molecule, please remember this point, in any molecule, any attempt to distort the bond length, right, whether it is compressing, whether it is the stretching, it will always requires the input of the energy. That means if you are stretching the bond, that means you are putting some energy into it. When you are actually compressing the bond, you are putting in some energy into it. So what we can do, we can always plot the energy against the displacement. Okay, and how we can actually plot the energy against the displacement, it is just like that. Here you can see, guys, here. So here this is you see the internuclear distance, this is the origin, this is the 0 actually, right? This is 0, this is the energy. Okay, and when why actually how I am getting this particular plot, I already told you, any attempt to distort the bond, whether it is the compressing, whether it is the stretching, it will require certain energy, and then we can plot this energy, which is like that in kilocalorie per mole, against the displacement from the your equilibrium distance, internuclear distance. So this is basically the R equilibrium, right? This is the R equilibrium, and here this point is actually the 0 point energy, right? This point is the 0 point energy. But before going further, you should understand what is happening here in that case. So please remember what I have done here in that case, right? So here you see, this is the hydrogen molecule, this is the chlorine molecule. So since this chlorine is the heavy molecule, so I have anchored this chlorine molecule to certain point actually. So we are not going to disturb this one. So I'll actually only move this hydrogen. I will stretch this hydrogen only. However, you can do the vice versa. You can put the hydrogen here, you can put the chlorine here. This will not actually make any difference, because ultimately we are actually finding the displacement, which would be the same in both the cases. Where you anchored the heavy, if you anchored the, see, it will not make any difference whether you anchored actually the heavy atom or the your light atom. Okay, so you can do the vice versa also, but I have anchored the chlorine here, and this is the R equilibrium. This is just this position here. So what can happen? This is the bond length, and I have stretched this, and this hydrogen is coming here actually. So this is the kind of the stretching, and when you do this actually, this is actually the internuclear distance, right? R equilibrium, and this R equilibrium changes, right? This value actually changes when you stretch this. So this new value is just like that, right? This distance. Okay, and in that case you can see this stretching is happening here, and here in that case you can find the energy of the molecule in this plot actually. What actually I can do the next, I can actually further displace it and put it here, so you will get the another value. So again you can see the difference, how the difference is there. You see, now this difference is like that. See, earlier was like that, and now it is like that. So if I keep on stretching this particular bond, then I can see this is epsilon 2, this is epsilon 1. I can have the many values. Okay, so this is actually the compressing or the extraction, right? This is how you can understand, right? So here this is actually the extension, which is the stretching, not compressing. So please remember this particular point. So what I actually have done here, see, I have anchored the chlorine atom on the one axis, which is here. Please remember, I have anchored the chlorine atom in this particular axis, and I am imaging the pushing or the pulling of the hydrogen atom closer to, that means I can pushing back this hydrogen here, and I can stretch further away from the chlorine atom, right? In both the cases the energy will change, right? So however you can do the vice versa, but I have anchored this one. This I have already explained to you, right? Now why we are getting this kind of the shape, this is another very important, and for biology students actually this is the big problem, why actually I am getting this kind of thing. So if I go back, guys, if I go back here, you can see right, this equation, you can focus on this equation, right? This is equation number 3. half of kx square. Mathematically, this equation is the equation for the parabola. Please remember, this is the equation for parabola. This is the equation of the parabola, and the shape of the parabola is always like that. That's why this kind of the shape I am getting here. Please remember, okay, since this equation 2 is the equation of the parabola, therefore this diagram is in the parabola shape, right? The zero curve, the zero of the curve, which is this actually, right? This actually point is actually x r equals to req, or basically x is equal to xeq. You can understand in that manner, right? So this is actually the displacement, nothing else, okay? And any energy, right, access to this, I am calling it as epsilon 2, and it is arises from the extension or the compression of the bond. So generally this figure shows that the one chlorine atom is considered to be stationary on x equals to 0, okay, and hydrogen will oscillate. Now this hydrogen will oscillate like that. So this will oscillate like that, okay. If the energy of the HCl molecule increased, so what will happen? Only this vibration will actually become rigorous or the vigorous, but you can see the vibrational energy will not change. Later we will see how we can explain this. Only this vibration is actually, see here, this vibration is low, here this vibration is high. If you stretch more, then this vibration becomes more high, and then more high, just like that. But the vibrational frequency will not change. Please remember, vibrational frequency will not change, okay. I hope this you understand. Now I'm moving to the next. What we can do, right here, for now what we can do, see, for this particular system, right, for this particular system we can calculate the vibrational energy. For this system we can calculate the vibrational energy. And how we can calculate the vibrational energy? For this actually you need to know the Schrödinger wave equation for the harmonic oscillator. So I am writing here Schrödinger wave equation, okay, I am writing in full. Schrödinger double dot, right, basically Schrödinger, this double dot actually represent au ki matra in Hindi, right? So this is Schrödinger wave equation, okay, for your harmonic oscillator. See, up to that point I have already explained why actually we have selected, or why we are taking this as harmonic oscillator, because bond behaves like that only. And if you want to calculate the energy of that system, then you should know the Schrödinger wave equation. And Schrödinger wave equation for this harmonic oscillator would be like that: del square psi divided by del x square. Mind you, this x is not the axis, this is the displacement. Please remember, in normal your say one dimensional box, or in the three dimensional box, your x, y, z and are coordinate, x, y, z are the coordinates, but in that case your x is the displacement, they are not the coordinate. Please remember. And this is your 8 pi square m over h, and this is your potential energy of the system, EV I am writing in that case, minus half of k square, kx square rather, this I have already given you, and psi equals to 0. This you should remember. This is actually the Schrödinger wave equation for the harmonic oscillator. What we can do, if you use this Schrödinger equation, then you can calculate the vibrational energy. So I am not going to see, it is very difficult actually to get the formula of that vibrational energy, but you should remember this point. If you use this Schrödinger wave equation, and by using this Schrödinger equation, this EV you can calculate, and when you calculate this EV, that means vibrational energy level, that EV equals to h nu Vib. This is nu, right? Vib means vibration, okay, and this is V, this is the vibrational quantum number, and plus half. This you can get actually. Please remember, this is vibrational frequency, this is vibrational frequency, okay, this is vibrational quantum number, this is the Planck constant, and this is the energy of that vibrational quantum number, okay. And this we have arrived by solving the Schrödinger wave equation for the harmonic oscillator, and this value is in the joules. This value is in the joules. So what you can do, you can convert. See, in the IR spectroscopy, we are not interested in the energy in the joules, but we are always interested energy in the form of the wave number, that is the what you can say in centimeter inverse. So if you want to convert this into the centimeter inverse, right? If you want to convert this into the centimeter inverse, what you can do, you can divide this equation. You can divide this equation by hc. H is the Planck constant, c is the speed of light, and you know h nu wave is already there. So again you can divide this by h into c, okay, and nu wave is already there, and this is your v plus half. So h and h, they gets cancelled, and this will become in the centimeter inverse, okay. So what you can do, you can see what for this, what you can do, you can use the different terms, right, which is actually your epsilon v. So epsilon v is actually ev by hc. So you can write this equation like that, epsilon v, okay, and this epsilon v equals to nu bar wave. Now it is in the centimeter inverse, and then your v plus half, it is in centimeter inverse. Please remember, right, these relations are very, very important, and I have already explained all these things in my previous lecture, for which I have already given you the link actually. I hope this is clear. There is no problem in that. What you can do, you can actually you can again find this actually nu wave vibrational energy. So what is the formula of this vibrational energy? Formula of the vibrational energy is actually like that. You can write here nu wave, or not actually vibrational energy. You can see the vibrational frequency, right? Nu wave, okay. Or you can say, see, energy and frequency are the same. They are interconvertible, so you can call it as any. Okay, either you can call it as energy or the frequency. So this is actually 1 upon 2 pi under root of k over mu, and it is in hertz. Please remember, it is in hertz. And hertz are again very we are not comfortable with the hertz. We need in the centimeter inverse. So for the centimeter inverse, what we can do, we can divide this nu wave by c, and this is 1 upon 2 pi c. When you put actually c here, so you know c would be in the centimeter per second, okay, and here k by mu, which is in hertz. So hertz is actually the centimeter inverse, so this will cancel out, right, and your formula would become, see, this whole you can write nu wave bar equals to 2 pi c under root of k over mu into centimeter inverse, okay. This mu is the reduced mass. Please remember, this is not the dipole moment, this is the reduced mass. So this is how you can get these things. These are very, very important. Now what we can do, we can learn one more concept here. And what is that concept? Say 0 point energy, right? 0 point energy. What is the 0 point energy actually in that case? So you know, you get this equation actually, what, epsilon v equals to nu bar V plus half. Okay, and it is in centimeter inverse, right? You get this actually. So what you can do, you can put V equals to 0. So definitely here you will get the 0, and here also you will get the 0. So you will get the epsilon 0 equals to nu bar is there multiplied by half, and the unit is the centimeter inverse. That means epsilon 0 equals to 1 by 2 of nu bar centimeter inverse. That means when your molecule is in the ground state, right, and zero vibrational state, then in the zero vibrational state also it will have the energy which is having the value of the half nu bar. This is something very important, and this is the difference between the classical mechanics, or you can say the classical mechanics and the wave mechanics. See, in the classical mechanics, your molecule, see, classical mechanics is not having any objection. It is not having any objection for a molecule to have the zero vibrational energy. But in the light of the quantum mechanical model, even in the ground state, your molecule will have this much of energy. This is something very important. Please remember is that the prediction of the 0 point energy is the basic difference between the quantum mechanical model and the classical approach to the molecular vibration. Generally, classical mechanism has no objection to a molecule possessing no vibrational energy. That means it can have the zero vibrational energy. But wave mechanics says that the molecule must always vibrate to certain extent if you keep the molecule even at the absolute zero. That mean, and this thing actually later it is experimentally proved later. This is something very important. So 0 point energy is this one, which is very important for you. So in the next class I'll go further how we can get the different kind of the energy, why the vibrational energy not changes when you actually increases the energy of the systems, only the vibrational frequency increases. All these things I will discuss in my next lecture. Okay, and then I will go further to explain the different kinds of the vibrations and all these things, the selection rules. So what you can do, you can recollect and you can learn this concept again and again, and once you memorize only this much of thing, then you will be able to solve the large number of the problems asked in the CSIR net examination, in the gate examination, as well as if you are doing your BTech from some certain university, then nowadays your BTech curriculum is also having in the first year these vibrational spectroscopy and NMR, all these things. So you can learn all these things from here. So I hope actually you understood the things completely. So I'll meet you in the next class, say maybe tomorrow or the day after tomorrow, right, with the more concepts. So that's it for today. But before signing out, I'm requesting you, please subscribe the tetrahedron chemistry classes, do share with your friends, and don't forget to like the video. Thank you very much. Thanks for watching.